Hello, my name is Matthew Newland. In this video, we're going to be generating plots for our vapor-liquid equilibrium phase diagrams at constant temperatures or given temperatures of 398 or 393 Kelvin and another constant pressure at 150 kilopascals. And these are given temperatures and our given pressure. And we're going to be using generating diagrams for our dew temperature and pressure and our bubble temperature and pressure using our given equations that we found in our dew temperature, dew pressure, bubble temperature, and bubble pressure for an ideal mixture. So, as you can see here, we already have all of our tools loaded up, and as you can see, we have NumPy as our as any arithmetic we need to do. We have our SciPy.optimize and our root function. We have our chemistry tools and you can see down here, we have benzene and toluene already preloaded in here. Next thing we have is our plotly.subplots, which is what we're going to be using the graph. And then we just have our plotly.io to plot everything on a darker graph so it can be more easily seen. So first, we're going to start off with defining all of our equations and what we found in our part one. So we're just going to define an equation. We're going to start with bubble pressure and then work our way down because some of our equations will rely on other equations to be calculated. So we're going to start with bubble pressure. So bubble pressure, to kick it off, will be quite simple. So we're going to have our first given value of x. And then, since we don't need anything else in this function, we're immediately going to return a function. And the thing we need to do is, since we have two things we're calling up here in our tools, we're going to need a NumPy sum. We're going to have a sum of these two, of what we're going to put down here. And what we're putting down here is our x value multiplied by our x is going to be a sort of a list of values that we're going to get. It's also going to represent one of our mole fractions for our equation, especially for our bubble pressure, because our equation for our bubble pressure included a liquid phase mole fraction. So we're going to have our liquid phase mole fraction multiplied by a chemistry tool, which is going to be our pressure in the vapor phase at a given temperature. So this is what we want for our first definition, or our first function here. And if you're wondering why are we using vapor pressure, well, our saturated pressure that we have that we had of an ideal of a pure substance is also the same thing as saying our pressure in the vapor phase. So we're just going to replace that variable with our pressure in the vapor phase at a given temperature. So the next thing we want to do is define our second function for our bubble side, which is going to be our bubble temperature. So we're going to have the same liquid phase mole fraction, but instead of temperature, we're going to have pressure. And we're going to do something a little weird here. We're going to define another equation and just set it as EQ or something, or just short for equation. Next thing we want to do is plug a V in and then hit enter again and then create another function. And why we need to do this is because what we're going to return here is our root solver. And we're going to use our root solver to find the value of our bubble temperature. So to solve this, we are going to need, first we need to set our temperature value is equal to the first value of an array. The next thing we need to do is then return this function. And what are we returning? We're going to set an array to return, and it's going to be our bubble pressure function, or excuse me, our bubble pressure function with our xy, with our x, our liquid phase mole fraction, and our temperature's already set in there, and then minus our pressure in accordance with our equation that we had from the beginning. So we're going to come down here and then return our last function. And then we're going to have a root solver, which is going to be our equation, our function from here, and this equation is going to be used as our vector getting put in here. And then we need our initial guess, so it's going to be 298.5, and we're just going to guess a temperature that's going to get plugged into here. And that is what we want for our root solver. And the thing we want to draw from this is the first value of our function, which is going to be just a value in itself. We're going to draw the value out of our root solver. That looks good. If I look through it again, yep, that looks pretty good. And then we're going to move on to our do list, or our equations for our do pressure. So we're going to do the same thing up here with our bubble pressure, but to make sure we're not going to conflict with variables here, we are then going to put a y value instead of here, instead of our x value. And since we're starting with pressure, we're just going to put our temperature is what we're calling. And then we are going to return the function immediately, and we're going to do something a little bit more differently than what we did with our bubble pressure, is that in accordance with the equations we found in part 1, we are going to do 1 divided by our sum, and then it's going to be, and within that equation, we're going to have another equation that's also getting divided by, so it's going to be y divided by our pressure in the vapor phase at a given temperature. So if that looks correct, that should be good. And then the next thing we need to do is do the same thing up here. So we're going to do something extremely similar to what we had up here. So we're going to write out our equation. Our due temperature is going to be our y, our vapor phase mole fraction with our pressure value given. And then we're going to define another equation for our vector. And then we are going to set t equal to the first value of the vector, and then return the function as our due pressure equation. So it's going to be y, and then, sorry, I just lost my train of thought, and that's going to be our temperature again, minus our pressure. And then and what we're trying to do now is then use another root solver, since we need to find our due temperature now, which is then going to be, is going to be our vector from our function up here, and then we're going to draw our function, or give an initial guess. And then we're going to draw the first value back out again. Now, all of our equations are set up, and now what we need to do is attempt to set up the rest of our values here in order to get our, all the values in order to get our graphs out looking properly. So from here, even though we have our equations, this is just a stepping stone to what we're actually going to do. The next thing we need to do is define our total mole fraction. So, and we know from our first mole our part 1 video, is that Z1 or Zi is going to be our mole fraction, is our total mole fraction of a substance, and knowing later on that's going to be a ratio between our this is going to help in our ratio between our liquid phase mole fraction and our vapor phase mole fraction. So C1 is equal to we need a list of values to plug in for our total mole fraction here of our first substance, which is benzene. So we're just going to assume that benzene is going to start at the bottom. So we're going to set a numpy in space, which is going to produce a set of values. It's going to start at 0 and stop at 1 and have 11 points in it. And this is going to allow us to determine the ratio between our moles and where our concentration of benzene is going to be, or the number of moles of benzene compared to toluene is. And then our Z2 is going to represent our mole fraction of toluene. So that's going to be, since we have a numpy lens space here, it's just going to be 1 minus our mole fraction. And this will then adjust, and for every value that's going to get spit out of our benzene fraction, or our benzene mole fraction, is then going to adjust our toluene mole fraction. And then and since we have a given temperature, T is going to be equal to 273.15 plus 120 to get us up to our Kelvin temperature, since 120 Celsius plus our plus 273.15 is going to get us up to our Kelvin value. And the next thing we want to do now is first thing we want to do is just start with what we have. So we have our bubble pressure. So we started with our bubble pressure first, so we're going to solve for that first. And in fact, it's just the easiest to go with. So the one thing we want to do now is then set up an array, or set up a series of values. So as I set up here, we're not using our vapor pressure, but now we want to quote unquote call this our saturation pressure. So we're just going to call this Psat. And the thing we want to do now is then, since we have a given temperature here and we have two values being produced by our chemistry props, we're just going to simply call our chemistry props. And this will spit out an array. And the next thing we want to do is then set a list, which is going to be our bubble pressure list. Oh, I don't want to capitalize that, list. And that is going to equal our mole fraction of benzene, which is Z1, multiplied by our first value of our Psat function, our Psat array. So that's going to be 0, and that's going to be added on to, and our bubble list is then going to be Z2 plus or multiplied by our value, our second value for toluene, which is going to represent toluene. So this is what we want for all of our list. And then the next thing we need to do is go down to our dew pressure list. And why do we need to do that before we start working on our bubble temperature? And the main reason we're doing that, because of these various root solvers that's being used in there. So we want to start, and we're going to solve both the bubble temperature list and the dew temperature list all in the same function, and it will not coincide with our dew pressure. So we're going to start with the simple stuff first. So the thing we want to do now is then we want to set a list for our dew pressure, which is going to be as such. So this is our list for dew pressure. And the next thing we want to do, is then make a for loop, which is going to be let's just call it our Y1 value. And then it's going up to a value of Z1, which we have up here. Oh, I had the wrong notation there. And the next thing we want to do is then we want to define an array. So we want to have an array that is equal to, we want a numpy array that is equal to our, actually before I do that, I missed one step. And since we have our y1 value acting in a similar way to our mole fraction, we want to have that being a just as well. So it's going to be 1 minus our y1. And that's acting in the exact same way as our z value up here, both of our mole fraction values. And then we're going to set another array as such. We're going to set another array, and that array is going to have two values in it. It's going to have y1 in our first part and our second y value in our second. And then the next thing we need to do is then, since we have a list defined up here, we need to add on to that list. Ooh, almost made a stupid error. We need to just call that list because it's going to conflict with our function up above. And then we want to use something called append, which means it's just going to add on to our list. And now the next thing we want to do is then use our do pressure function up above. So it's going to be do pressure, and then it is going to have this numpy array in it. So what we want is our y value, which what we have up there, and then we're going to have our temperature value. So this is making our list. Okay, now the next thing we want to do is now we're going to move on to our bubble pressure, or excuse me, our bubble temperature and our dew temperature. So we're going to define those as such. So bubble temperature will come first. It's just a list, or sorry. And then we're going to have our dew temperature. So I am just rushing this right now. Did not mean to do that. And since we have our list defined right now, and the main component we want for this is our pressure values. So our pressure value is a given value. So going back to our original, we want 150 kilopascals. So we're going to set that as such. So our pressure is going to be equal to 150 to our exponent of 3, which is just converting that to kilopascals. And then we're going to do the same thing up here. So we're going to set another function, but since we don't want our variables to start, you don't want our variables to start conflicting with each other. So we're just going to play it safe and then set this with another variable. So it's going to go up to our same z1 value. And then what we want to do now is then do a similar thing and just sort of just repeat what we want from here. The next thing we're going to do now is then have our xy2 minus, or is equal to 1 minus our xy value of 1. And then this acts in the same way as what we did up here in our z values, and our mole fraction values, excuse me. And then the next thing we want to do is then have our append list created. So we're going to have our bubble t list append, and then we're going to set in what we want to do now is call our function. We're going to call our bubble t function and then set a we're going to set a for our first value x, we are going to then that's why we're calling it x and y, is because it's going to refer to both our liquid phase mole fraction and our vapor phase mole fraction. So we're going to call our bubble temperature function, and we're going to set a numpy array as such. So it's going to be xy1 and then xy. And then we're going to call our pressure value, which we already know is going to be constant. So this is our bubble temperature appending list, and then we're going to need our dew pressure appending list. Sorry, it's going to take me a little bit to write it out. And then we have our numpy array. Actually, since we're doing the same exact thing, since we have already accounted for x and y, and that's not going to change, we are just going to copy and paste that into our new function as such. If everything looks right, then we're good to go to move on to our graphing. So as per usual, we're going to define our graph as fig is equal to make subplots. And we want to have one row, we have only one row that we're going to use, but we're going to have two columns. Since we want to represent two particular graphs, or more particularly, we want to represent the relationship between our various lists. More importantly, we're going to represent the relationship between our bubble pressure and our dew pressure on one graph, and then our bubble temperature and our dew temperature on one graph, or on a separate graph from our pressure values. So from here, we can then start to make our function. So it's going to be fig.add underscore scatter. And then our x value is just going to be equal to our z1, our liquid phase mole fraction, because it's just going to represent how far. Since we have a list of values for our z1 value, it's going to start at 1, and it's going to start at 0 and then work its way up to 1. And that's why we want we want z1 as our x-axis list of values. And then our y value is just going to be the list we made for our various temperatures and pressures, or bubble temperatures and pressures, excuse me. So we're just going to start with our bubble pressure list row, and then we're going to set that to row 1 and column 1, and we're going to name this particular graph or this line as just our bubble pressure. So, and before I move on, I'm just going to call this just to make sure if everything's working correctly. And voila, it is. So now since we're just going to repeat the same thing over and over again, we're just going to copy and paste our function again, call this our bubble temperature, and then we're going to call this our bubble temperature list. However, we're not comparing our bubble temperature and our bubble pressure. We need to set this to our second graph, and then we're just going to write out the function again, which is going to be fig.add scatter, which is going to be x equal to c1. And then we're going to start digging into our dew values, which is going to be our dew pressure list. With our first row, and then it's going to be our first column again, and name that line dew pressure. So that looks all good. I'm just going to call the function to make sure everything's right. And as you can see, we have a line connecting them. Now the next thing we want to do is then copy and paste this whole function as we did before. And then we're going to call this we're going to call or set that to our second function, or set that to our second graph, and then we're going to call this dew temperature, and then we have to switch the list over as well. Oh, I messed something up. For some reason, we're not getting a set of values right now. Why is that? So something is obviously wrong with our dew temperature list. So we're going to go back up. Oh, I see what I did. I did not call the right function. There we go. Okay. Now, once we have everything working as it should be, These two graphs represent the relationship between our bubble temperature, our bubble pressure, and our dew pressure, and see how our mole fraction changes depending on where we are in the actual equation. And this does the same thing for our dew pressure and our bubble pressure. And these two graphs represent the relationship of our mole fraction. And more importantly, it represents our different points at which our Z1 axis is changing. So as our concentration of benzene is getting higher, our concentration of toluene is getting lower. And the same thing happens over here depending on where we are with the pressure, with a constant pressure, over here, since this is our pressure values or temperature values, this is going to be a constant pressure, and then this is going to be our constant temperature. This represents the concentration and how it's changing with what I said before, benzene getting higher, toluene getting lower, and then vice versa.